My name is Owen Haynes, and today I'll be presenting Physics 2112's Lab 1 charge tapes. Okay, so the purpose of this lab was to observe and calculate how differently charged pieces of clear tape interact with each other to gain a deeper understanding of Coulomb's law. We did the experiment using simple household objects like Scotch tape and a ruler. We set up the experiment, observed what we saw, recorded what we saw, and then using what we recorded, we modeled these interactions using GlowScript. And then ultimately, the result of this lab was that we found that the charge of each tape was around 5.11 times 10 to the minus 9 coulombs. So first, we went through some qualitative experimentation. The way that we actually charged the tapes is we put a long strip of tape on the table, and then we took a U-tape, which we placed on top of that piece of tape on the table, and then we ripped it off. And the idea is that the U-tape, as shown in the diagram on the left, is now charged. And theoretically, if you hang this piece of tape from the table, and then you move your hand next to it, you will see that the tape is attracted to your hand. And in fact, yes, we did see this. As you can see in the video on the left, the tape was attracted to our hand, and then also two of the charged tapes repelled each other. So that was our qualitative observational experiment, but now we want to actually gather some data and do some calculations. So we set up this experiment, as you can see on the left, where we charge a tape B on the top, and then we grab another charged tape A on the bottom. We take tape B and we suspend it in air, and then we bring tape A underneath it, and since they're both charged with the same charge, they should repel each other. So as you can see on our right, this is our setup that we had. We had the tape suspended between two erasers, and we just brought up the other tape by hand, and then we measured the distance between the tape underneath with the tape on top, and then that allows us to do some computations. Now, the way that we actually did these computations, we're using these two fundamental physics principles. So first, we have Coulomb's law, which describes the force that two charged particles exert each other based on the charge of each individual particle, represented by Q1 and Q2, and then the distance between them, represented by the r squared underneath, and then the vector r. And you can see underneath is a little diagram that describes the placement and the charges of the particles. Then we also have Newton's second law, which is the sum of forces equals mass times acceleration, which will be important for the free body diagram that we're going to set up in the next slide. So in this slide, I set up a quick free body diagram to balance out the forces. As you can see, tape B is our system, and tape A is the surroundings, which exerts force on tape B. When tape A was moved up underneath tape B and pushed tape B up, after tape B was pushed up, the system was in equilibrium, which means that the force due to the electric field and the force due to gravity should balance out. There are a lot of assumptions that we're making in this model. First of all, air resistance is ignored. This is pretty reasonable because we're inside and there's not much wind or anything like that. Tapes A and B are treated as point charges with the charge located at the centers of them. This is also okay because in the far field, a collection of the same charge can be treated as a single point charge. And also, it is just unreasonable to compute every single individual charge on that piece of tape. So it is easier to just distill it all into one single point charge for the model. And then tapes A and B are assumed to have the same charge. This is because they were made using the same method of placing that piece of tape on the table and then pulling it up. So having the same method, they should have around the same charge. So we set up this free body diagram, and then we use Newton's second law. Sum of forces equals mass times acceleration, but there's no acceleration, so we have the sum of forces equals mg minus the force to the electric field equals 0 because there's no acceleration, and then we just solve for Fe. And then on this bottom line here, Fe is equal to the equation shown in Coulomb's law. Then we need to solve for Q because we're looking to find the charge of the tape, and then we have this. Q is equal to the square root of mg d squared over k. Right, so now that we have that formula, we can get to our code and actually model this scenario. So first, we set up our constant and our measured quantities, the most important being the mass of the tape to calculate the force due to gravity. And then this bottom line here, line 13, is just that equation that we found earlier. So that computes our charge of our tapes. And now we can use this electric field function, which is just Coulomb's law, where you can plug in your particle charge and particle location where you're observing, and then it spits out the electric field at that point. So we can compute the electric field exerted by tape A on tape B. And then down here, lines 25 through 35 are just visually representing those particles' interactions using the code. So after running the code, we find this to be our result, where tape A is exerting an electric force on tape B, but that balances out with the force due to gravity. So this model is not exactly representative of what was happening in the real world. As described earlier, a lot of assumptions were made when setting it up. And then also we have the sources of error here on the right. First one is that when handling the tape, the charge of each tape likely changed. If it accidentally rubbed up against an object or we touched it with our hands too much, electrons could have jumped to and from the tape, changing its overall charge. And then a lot of unaccounted forces in the surroundings and internal to the tape. So tape B is not just free floating in the air, it's actually being supported on either end by those erasers. And then also the internal tensions of the tape. The tape is really light, so we found that the tape could kind of support its own weight. So a lot of error and assumptions happened between the model and what we actually observed in the real world. What if the electrons had positive charge and protons had negative charge? What would change about the observations you made with your tapes and other charged objects? So this would not change anything. Since protons and electrons have the same magnitude of electron charge, the same exact force would be exerted on tape B, and everything would remain the same. Why is it important to handle the charged tapes as little as possible? What happens when the charged tapes come into contact with your hands or other objects? So as described earlier, in the errors that could have happened in this experiment, if the charged tape contacted other objects or hands, electrons could be transferred to and from, which would then change the charge of the tapes.